So, hello everyone. So the goal of the series of lecture I will give is to discuss a recent joint work with Johannes and Schultz, which will be online soon. And this joint work takes place in the setting recently developed by Farg and Schultz for with the purpose of geometrizing the local Langlands correspondence. So, in fact, this series of lectures is mostly a pretext to give you some kind of motivated introduction to all this geometrization program of Farg-Schultz. But of course, it will be a very light introduction. The idea of geometrizing the Langlands correspondence has been, it has a long history, so it has been understood how to do it for the local Langlands correspondence over local fields of positive characteristic or characteristic zero only very recently. But it is inspired by a much older story, which has to do with the Langlands program for function fields. So, and what I want to do today is to explain a little small part of this story, because everything we will do later at the very end of these lectures will be in fact motivated by some analogy with the situation for function fields. So what is the setup? So let me fix f, a function field, over a finite field. So algebraically, that just means that I choose a field transcendence degree 1 over a finite field. But more geometrically, the way to think about it is that we have a smooth projective curve X geometrically connected as well over finite field Q, which I will often in this talk denote by the letter small k, such that the field F is simply the field of neuromorphic functions on X. So, for example, if you take X T1 of K, then the field that you get is the field of rational fractions in one variable T. Okay, and associated to F, I have the ring of adage of F, which is the restricted tensor product noted with a prime of the completion of F at all the various spaces of F, which are in one-to-one correspondence with close points of the curve X. And it contains O as a maximal compact, which is just the product of all close points of X of the ring of integers of the valued field Fx. Okay, so from it has been understood since a long time that from the arithmetic perspective, function fields behave exactly like number fields. That is, finite extensions of the field of rational numbers Q. And in particular, all the Langlands program makes sense for them as well. So all the conjecture you can formulate in the Langlands program for number fields, you can also formulate them for function fields. So of course, from the perspective of someone interested in number theory, the case of number fields is more interesting. But function fields have a big advantage over number fields, which is actually visible on the blackboard, which is the fact that they are naturally associated to a certain geometric object, namely this smooth projective curve X, to which F is the field of meromorphic functions are. And this is actually a very powerful tool because we can try to prove various arithmetic statements about F using these geometric objects. And the talk of today is an illustration of this principle. But for this, I need to first recall a particular instance of the Langlands conjecture sense. I will only deal with the simple case where everything is ramified everywhere. So let me fix. So F is fixed. And now let me also choose some integer n bigger or equal to 1 and a prime L different from P. So P, so my finite field K, FQ is such that Q is the power of P, and I choose a prime L which is different from P. So in the unramified case, Langlands correspondence is known, and I will only state one direction. Langlands for function field. So let me fix sigma representation of the Galois group of F valued in GLN of 2L bar, where L is a primary fixed and N is integer also fixed, which has the following property. So first of all, I want sigma to be continuous, where the Galois group is endowed with its Krull topology, which makes it a profinite group. And this one is endowed with the usual way with the Ladic topology. The second condition I want to put is that sigma is geometrically irreducible. So the adjective geometrically means that if I extend scalars from F to the extension of F coming from replacing the base field K by its algebraic closure, I want to set sigma seen as a representation of the Galois group of F bar over F of K stays irreducible. So it's slightly stronger than saying sigma is irreducible. And finally, the third condition I want to put on sigma, which is the one which explains the adjective and ramified title of the theorem, is that sigma is everywhere unramified. So in other words, for any close point x of x, if I consider the restriction of sigma as a Galois group, as a decomposition group at x, it is trivial on inertia. So it's just given by the up to conjugation by the image of the probability. Okay, so these are the assumptions I put on sigma. And what the theorem says is that then there exists a unique up to scalar. So element of QL bar cross, and non-zero function. So let me denote it by F sigma. So F sigma is defined on GLN of the address of F, and it's left invariant by GLN of F, which I recall you can embed F diagonally inside a string of addends. And I also want it to be right invariant by maximal compact GLN O. And this function takes value in QL bar. And okay, of course, the theorem is not finished. I want to impose some condition on this function. So, erase. What are the properties of F sigma? So the first property is that F sigma is cuspidal. So this is an analog in this function field setting of the cuspidality condition that maybe you are familiar with in the setting in the framework of modular forms. So I won't spell out this condition, but I just want to point out that it's related to the second assumption I had put on sigma, which was the fact that sigma was geometrically irreducible. And the other condition is that F sigma is an Ecker eigenfunction for sigma. So what does that mean? It means that for any x in x, and for any integer I between 0 and n, if I look at Tix of F sigma, which by definition is the function which sends an element g to the integral over the following double coset. So you look at the diagonal matrix with pi x I times on the diagonal on the one, where so pi x is a given uniformizer at x, my close point, which I fix, and I take the double coset for the translation action by GLN of x, the maximal compact inside GLN of x, and I integrate over this double coset the function F sigma, where d of h is normalized measure on GLN of x, normalized so that the integral on the maximal compact of constant function is just 1. So the volume of GLN of x is 1. Okay, so this was a definition of this. I have any function f and double coset, and I want to produce another such function for my given choice of I and x. So this is how it is, how this is done. And this operator Tix is called an Ecker operator. And the condition I put, the condition of being an Ecker eigenfunction for sigma, means that F sigma is an eigenvector for all these Ecker operators with eigenvalues, which are given in terms of sigma by the following recipe. So first, there is a certain normalization factor, which is not so important for us. So here, Qx is the cardinality of the residual field of X, the residual field of the local field Fx. And then the important term is the trace of the highest exterior power of sigma of X times F sigma. Okay, so as I said, F sigma is required to be an eigenvector of these Hecke operators, and the Hecke eigenvalue up to this factor is determined by by the restriction of sigma at the decomposition property. So recall that sigma is assumed to be unramified everywhere. So in particular, here Frobenius of X will denote just any lift of the Frobenius element on the Galois group of the residual field at X. So this is well defined up to conjugation, but I'm only taking the trace. So this expression is well defined. Okay, so this is the meaning of this second condition. So I repeat, this first condition of cuspidality is related to the assumption that sigma is irreducible. And then there is this key condition that F sigma is an Hecke eigenfunction for sigma, which is the condition which somehow relates explicitly the Galois representation sigma if it's at the beginning to this automorphic function. Okay, and this has, if you know about the Satake isomorphism, this has a much better formulation, which is less explicit, but conceptually easier to understand. But let me ignore this one. But this may, if you never saw it before, this may look like a strange condition, but there's a nice way to, more abstract way to think about it, which makes it more natural. Okay, so let's try to see how to construct such a function. So, well, okay, if n is 1, so if I'm just looking at GL1, and then somehow you have no choice. You have to define the requirements of the theorem forces the function F sigma to be the function which sends AX in F cross to the product of X in X of sigma from X times the variation of the elements AX at X. So note that by definition of the restricted product, this quantity will be 0 for almost all X. So this product is well defined. And well, it also Wright invariant by multiplication by O cross. What is not obvious in the content of class field theory is the fact that it is also left invariant by F cross, right? Okay, but I will come back to this issue later. Let me know stick to the general case, because in the general case, it's not even obvious how F sigma should be defined. So how to construct F sigma? So in fact, there is also, in general, a natural candidate for F sigma, even if it's less obvious to find it. And let me now try to explain how that works. So this will involve some Fourier theory. So to explain that, I need to fix omega, a meromorphic one form. So some elements on omega 1 of f over the base field, finite base field k, which is non-zero. And also I need to choose psi, an additive character k, which takes values in QL bar cross. And the choice of psi determines something which I will denote capital psi, and since there is no risk of confusion, which goes from f, so AF modulo f, to QL bar cross, which will be again a character. And what does capital psi do? It sends the collection AX indexed by close points of x to my small psi, evaluated on the sum over all x in x of the trace from kx to k of the residue at x of ax times my differential from omega. So kx is a finite because x is closed. Kx is just finite extension of k, so I take the trace of this quantity which lives in the residue field at x, k is one form on fx, and I just take the coefficient of pi x minus 1. Pi x is my local parameter. Okay, all right. So you can check this is well defined. And the consequence of Contrier duality is the fact that AF is the ring of adels is self-dual, is the fact that in fact all the characters of this quotient are of the form psi gamma, where psi gamma is the character which changes y to psi of gamma times y, where gamma is an element of. Okay. So AF, as I said, is self-dual for Contrier duality. So using the exact sequence involving f and the quotient of the adels by f, this implies that the Contrier dual of AF mod f is just f itself, and explicitly this takes this form. So all characters of this locally compact abelian group are of this form, and they are like exactly parameter. So let's momentarily assume that n is 2. And let me take f, a smooth function. So smooth here just means locally constant on GL2 of the adels, taking the value in QL bar, and which is left invariant by multiplication by GL elements of GL2F. And then, whenever I fix, let me fix the G, some element in GL2 of the adels. Then I can write, using the reminder I just gave, the Fourier expansion of the functions on NF mod NF, where N is a subgroup of GL2. the upper standard upper unipotent, which is given by all matrices of the form 1, 1 on the diagonal, and nothing below the diagonal. So what is it? As a group, this is just isomorphic to GA. So this quotient here is the same thing as F mod AF. And let me consider the function which sends an element n inside this quotient to F and G. So this will be a function taking value in 12 bar again. Okay, which is of course well defined because F was assumed to be GL2F invariant, so in particular NF invariant. Okay, so what happens if I consider the Fourier expansion of this function? Okay, well, because of what I said before, I get the following. So I fix my element G. Then I get that for all n prime, say, in n observables, I have that F of n prime G is given by the sum over gamma in F of well, the Fourier coefficient corresponding to this gamma. Integrals of F and G against psi gamma minus 1 of n dn times psi gamma n prime. Okay, so this is just the Fourier expansion of F using the descriptions of the characters of this quotient I gave before. And now let me take n prime to be 1. Let's assume that F is cuspidal. So I did not say what it means precisely, but let's take this as a black box. And just remember that the cuspidality condition, exactly like in the theory of modular forms, implies that the Fourier coefficient corresponding to gamma being 0 vanishes. So this means that I get, again, by taking n prime to be 1 and using cuspidality, I can forget about the first, the coefficient corresponding to gamma equals 0. And then, okay, so I have, again, this integral, which I write again. F n j psi gamma minus 1 n dn. Okay, and then I take n prime to be 1, where this isomorphism corresponds to the origin here, so the element 0, and psi was an additive character, so psi gamma as well. So psi gamma evaluated on and this element is just 1. So I just get this form. So this I can rewrite as follows. So it will be the sum, still over gamma in F cross, of WF psi gamma 0, 0, 1 times G, where what is this function WF psi? So W stands for Whittaker. It's a function which sends G and F F and J psi minus 1 of n d. Okay, so here to go from this line to this last line, and implicitly, if you check the argument carefully, you will see that I'm actually using that the function f is invariant by left multiplication by an element of this form, where the element cos belongs to f cos. Okay, so what does f psi looks as a function? So w f psi. So it's a smooth, so locally constant function on GL2 of the Ladels, which by construction has the property that it belongs to a space I will denote like this, that n of the Ladels psi, where this is by definition the space of smooth functions W from GL2 of RF to QL bar, which have the property that Wnj is psi of n Wj for all j in GL2 of the Ladels, and n in n of the Ladels. Okay, so this is very easy to check that W psi belongs here. Okay, so this is what this Fourier theorem gives us. For any smooth function on GL2 of the Ladels, which is left invariant by GL2F, I can write its evaluation on some element G as a sum indexed by elements of F cross like this. Okay, in fact, if you look at the argument, you see that the only thing we have used is that F is invariant. Let me just write it as a remark. We only use that F is left invariant by the subgroup M2 of F, or maybe maybe I will call it P2. Let's say P2, where P2 inside GL2 is a subgroup formed by all matrices, invertible matrices of this type. Right? Because I mean, we used obviously the invariance by multiplication unipotent matrices to even make sense of this Fourier expansion. And then, as I said, in the very last step of the computation, we also use invariance by elements which are diagonal with anything on Z1. But this is all we use. And so, in fact, so now back to general N. So I don't assume that N is 2 anymore. But then you have to work more, because if you look at the upper unipotent subgroup in GLN, it's not abelian anymore. So you have to do some inductive argument. This was done by Shavika. And you can prove the following statement. So for this, let me again, before stating the result, introduce one more notation, so which is just obvious generalization of what I just did in this remark. So that Pn inside GLN be the subgroup which is formed by all matrices which are like a block of size n-1, a matrix in GLN -1, then 0, then whatever you want here, and 1. So it's called the mirabilic subgroup of GLN. And so here is what I think it's Chalika who first put this result, which is generalization to all n to, I mean, something we basically proved for GL2, but not fully. So there exists well, let's write it this way. The map phi which sends W to the sum over gamma in GLN minus 1 F divided by n minus 1 F for the subgroup of upper unipotent matrices in GLN minus 1 W gamma 1 0 induces so the GLN AF equivariant isomorphism between this space of Whittaker functions that we introduced for GL2. And I don't repeat the definition, which is for GLN exactly the same. So the only thing I have to say is how you see psi now as an additive character of this group. And the recipe is just the following. So here psi, I'm using notation, denotes character, which sends a unipotent matrix of size n to psi of the sum of the elements which are just above the diagonal. So if n is 2, we just recover the previous definition. And this is here capital psi. Okay, so the claim is that this map phi induces a GLN F equivariant isomorphism between this space of Whittaker function and the space of smooth function, which are cuspidal on GLN of the adels, and invariant on the left by the action of the mirabolic, so the F points of the mirabolic circle in GLF. Okay. So, at least when n is 2 should be quite plausible now, I hope. So what's the point of this theorem? Well, we try to attach to our Galois representation sigma certain automorphic function. That is a function on GLN of the adels, which is right invariant by GLN O and left invariant by GLN F. And this result tells us that, so in particular, I can just forget about this right invariance property, and I can just see such an automorphic function as something living on the right-hand side. And the theorem tells us that another way to think, everything is compatible with the action of GLN of the adels acting by right translation. This proposition therefore tells us that to construct an element here is the same as constructing something here and applying this operator phi. And why is it better to work on the left-hand side? Well, the reason is that here you have this left invariance condition by something coming from the field F itself, which is diagonally embedded in the adels. So it's rather difficult to, if you construct a function, checking this left invariance property can be tricky. Whereas here, the condition you have, so of course, we are not looking at all possible smooth functions on GLN of the adults. You have this condition to check, but it's really a local condition. It can be checked at each place is separate. So therefore, it becomes a purely local problem. And let's explain how this works in practice. So far, everything works in general without any unramifiedness assumption. But so maybe I should point this out. Everything so far works without assumption, by which here on the automorphic side, I mean without assuming any right invariance property. But the following theorem is really crucially using this property. Namely, it tells us how to construct local Whittaker functions. So it's a theorem of Kasselman and Shalikar. So what's the statement? So for each close point of the curve X, so in other words, for each place of my function field F, and for each conjugacy class gamma in GLN QL bar, Kasselman-Shalikar claims that there exists an explicit, so you can write down an explicit formula. I won't do it, but you can make everything explicit. Functions W gamma X, which goes from GLN of the completion of F at X to L bar, and which has the following properties. So, so first, certain normalization assumption. I want W of gamma X evaluated at 1. So in particular, this element is non-zero. Then I want this W gamma X will be invariant by the multiplication action on the right of the maximal compact GLN OX. Then I also want that for any n which belongs to the fx valued point of the upper unipotent subgroup, and for all g in GLN of x, I want that W of gamma X and G is given by psi. So here my psi is, the context should always make clear what I mean by psi, even if the writing does not really help distinguishing between the various psi I had. So now it's my original small psi I had fixed at the very beginning. So I take the trace from kx to k of the residue of n times omega and times W gamma X of J. Because it's a kind of local Hecke property again. Sorry, no, excuse me, it has nothing to do with the Hecke property. It's just the local version of this equivalence condition we had for Whittaker functions before. The Hecke property is coming now. So I want that for all I from 1 to n, this Hecke operator I had before, which is exactly defined in exactly the same way, applied to W gamma X is Qx times the normalization factor as before, trace of wedge power I of this conjugacy class gamma times W gamma. Okay. And moreover, W gamma X is unique, characterized by this property. This property. And I repeat that you can make this local Whittaker function completely explicit. Okay, very good. So what can we do with this? Well, now we can, from this local Whittaker function, so local here, local Whittaker refers to the fact that they have this equivalence property, but somewhat locally at this close point x. I can construct a global Whittaker function. But to do that and to answer my original question, I need, of course, to do that in a way which is related to the Galois representation I have. So let sigma be my Galois representation, so as the main theorem of today. And so in particular, sigma is everywhere on ramified. And then let me define W sigma to be the function on GLN of the Hadel, so it's this function, 12 bar values, which sends G to the product over all X in X of W sigma of X, X evaluated at. So G is a collection of invertible matrices of these coefficients in Fx when it's varied. And so in particular, by the assumption that sigma is ramified, I have this well-defined conjugacy class, sigma of X, which is a gamma to which I apply the Kassilman-Shalika theorem. And I get this local Whittaker function. And then I take the product, which again is just a finite product, so it's well defined. And I will now set F prime sigma to be the image by this operator phi in the result of Shalika applied to W sigma. So observe that W sigma is obviously satisfies this equivalence property simply because it's a local condition, and this just boils down to this property of this local functions W gamma X. And moreover, because phi was assumed to be, by the proposition, is GLN AF equivalent isomorphism for the right translation action, you see that F prime sigma is, well, okay, so Oedipus pedal, it's invariant by left multiplication by something in the mirabolic, the F points of the mirabolic. But because all these local functions were GLN OX equivalent, and because capital phi is equivalent for the right translation action, this is GLNO invariant. Okay, and moreover, it has the desired echo property. So for all X in X, for all I between 1 and n, you have that CIX applied to F sigma is indeed QX minus I minus 1 over 2, the trace of wedge power of sigma of X, sorry, it's a prime, times F prime sigma. Again, this follows from the construction of this local Whittaker function. And in fact, because phi is an isomorphism, and because of this unicity property in the Kassilman-Shalika theorem, you see that well, f prime sigma is a unique function here with these properties up to scalar. Okay, so back to our original problem, back to the theorem. What does that tell us? Well, we have produced a function f prime sigma, which has almost all the desired properties, and its particular is unique up to scalar with these properties. But we are not done yet, because what is missing is here f prime sigma is only left invariant by the f points of the mirabolic, and we want the function f sigma to be GLN f left invariant. So because of this unicity statement, we see that, well, to prove the theorem, so the question now is simply the following. We need to see that this function f prime sigma, we just defined, is left GLN of f invariant. Okay, so you see, in the case where n is 1, all these constructions are unnecessary, because directly the statement of the theorem tells you uniquely pinpoint what f sigma should be. I gave you the formula, and the only difficulty is proving that it's f cross invariant on the left, right? Everything being abelian. So here, now we are for general n in a similar position. We have this natural candidate. We know it has to be the right one if the theorem is true. So all the only thing we have to check is this invariance property. Okay, in fact, surprisingly, it's everything we have done before was quite explicit, but this is surprisingly hard to prove. I don't think there is any proof in this spirit. And the way found by people to prove the theorem is to use some geometry. So it seems impossible to check this directly. So we will reformulate everything in geometrical terms and try to use some geometry to solve this question. So to give an idea of how that works, let me write this program. So when n is 1, okay, so as I said, it's basically classical theory, but you can also, in this situation, give a geometric argument, which is due to D. And this then is inspired work of Riemann, which was then generalized by Lomont to all n, bigger or equal to 2. And the slogan is to replace functions by sheaves. To explain what that means, let me recall the following simple but useful observation. This is called the function sheaves dictionary in the literature. Whenever you have Z, which is a scheme or even a stack over the finite field K, and whenever you have a complex K, and D at Z to a bar, here D at denotes the bounded constructible derived category of analytic sheaves on this scheme, on this stack Z. You can attach to K to this complex a function called the trace of K, which is defined on the rational points, the K points of Z, and which takes values in QL bar. And what this does is that this sends an element X in here to the alternated sum of the trace of the Frobenius at X on the ith homology sheaf of K. Okay, so for each I, this ith homology sheaf, it's an étal sheaf on Z. So in particular, my K point X, I can just pull back this sheaf along X to get an étal sheaf on spec K, which is just the same thing as QL representation of the Galois group of this of K. And so in particular, it's well, this Galois group is topologically generated by this element from X, and I take the trace of this Frobenius element on the stalk of my sheaf at X. Okay, so whenever I have a sheaf, an étal sheaf on Z, or more generally complex of étal sheaf, I can attach to it function on the K rational points of Z. Okay, so the idea will be to try to construct our F sigma as a trace function attached to a complex of sheaves on a certain stack over K. So to give a meaning to this, I need two basic but really fundamental observations. So the first one is on the Galois side. So a sigma has in the theorem, so a continuous, geometrically irreducible, everywhere unramified Galois representation is the same thing as a rank n, well, again, geometrically irreducible. So, I mean, the irreducibility condition on both sides match up. Least sheaf, so least QL bar sheaf, L. Why is that? Well, simply because by one étal, X, so such a least QL bar sheaf L will just be the same thing as QL bar continuous representation of the étal by one of X. But this is exactly the same thing as the unramified part, maximal unramified portion of the fundamental group. Sorry, the Galois group of F. Okay, so sigma, the key here is really the regular unramified assumption on sigma, which tells us that sigma factors through this quotient, which is the same as the étal by one. So you can know, if you want, you can just think to sigma as a locally constant sheaf L on this smooth projective curve X. And what about the other side? So what about this F sigma? So here the key observation is due to Pei. So let's look at the moduli stack burn n of rank n vector bundles on X. In other words, it is a stack which sends a scheme S over the base sheet K to the group of rank n vector bundles on X times S over K. So this is a nice smooth artin stack. And I can consider the K points of this stack. So this just corresponds to, so okay, like how, like when I take the K points, this will just correspond to, I mean, I could see it as a group, but here let me just see it as the set of isomorphism classes of rank n vector bundles of X. And the observation is that this is in natural bijection with this double coset appears in for the domain of this automorphic function of sigma I try to produce. So, I mean, this gives a very nice geometric interpretation of this double coset. And the basic idea, I won't prove this statement, but the basic idea is simply that if you have a rank n vector bundle in X, you can choose a trivialization at the generic point and choose a trivialization on each formal disk around each close point of X. And so once you have made such choices, if you fix a point, close point X, you can compare the trivialization on the formal disk around this point you have chosen with the generic trivialization you also have chosen. And to go from one to the other is the same as giving yourself an rank n, size n invertible matrix with values in coefficients in Fx, corresponding to the punctured disk, punctured formal disk around X. So for each X, you get a matrix in GLN Fx, which is almost everywhere trivial, and so you get an element here. And then if you forget these choices of trivialization you have made, it just amounts to dividing on the left by GLN F corresponding to the choice of the generic trivialization. And here modeling out by GLN corresponding to these choices for each X of trivialization on the formal neighborhood. Okay. And so now the strategy developed by Greenfeld and Lumont has two main steps based on these fundamental observations. So maybe let me write the goal. That will be quite clear. Now we will try to construct, to find F sigma as a trace of haute L, where haute L will be a complex of detached shift on this moduli stack point. Okay, so so sigma corresponds to a least shift L on X, and what we will do is we will attach to this least shift L complex of L-adic shifts on the stack bulb N, so that when we take the trace of this complex in the sense I recalled before, we get a function which by construction will be defined in this double coset, and which will have the Helker property with respect to sigma, and also satisfies the spirality. So that's the idea. Of course, now the main difficulty is to construct this complex of shifts, which may a priori look even more complicated than constructing the function. But actually it works. And the strategy has two steps. So first we will construct haute prime L, not haute L, which will be a bounded constructible complex on not on the N, but on some auxiliary moduli stack, Von prime N. So this is the moduli stack, Von prime N parameterizes pairs E, S, where E is a rank N vector bundle, and S is an injective map from the dualizing shift on X towards E, so I'm not exactly sure about the correct normalization here, but never mind. So this is what Von prime N parameterizes. We want to construct this haute prime L, depending on L, in such a way that the trace of haute prime L, so the K points of this auxiliary moduli stack will be exactly given by not by GLNF, no, by the same thing where you replace the quotient on the left by the quotient by the Mirabel subgroup of size F. It will be exactly the domain where F prime sigma was. And so we will try to construct with prime L in such a way that its trace is given by F prime sigma. And then the harder step, which was done by Drinfeld when n is 2 and by Frankel-Getz-Coe-Belonen when n is bigger than 2, is to prove that what prime L descends to a certain complex of L, which is the one we want, and then n, by using the geometry of the map. So there is an obvious forgetful map from prime n to burn n. I just forget the section S. I just remember E. This gives me a map from burn prime n to burn n. And the idea of step 2 is to try to use that to prove, sorry, that those prime L is in fact the pullback of a certain complex of quadratic sheaves on burn n, both L along this map. And then the trace of haute L will be the desired function of sigma. Okay, so I'm basically out of time, so let me just say that step 1 is basically redoing everything we have done before with functions, using the sheaf functions dictionary as some kind of useful guide. Or, I mean, all the manipulations you can do on functions, they have some analog using the 6-functor formalism on the category of complex of eta sheaf. And so the basic idea of step 1, this is what Rayfeld and then Lumont were able to do, is, roughly speaking, to imitate what we have done before with the Fourier transform in this geometric set. And then step 2, as I said, is much harder. I mean, as written, the claim is not even rigorous because you have to say more to like uniquely characterize this haute L. And there is what some of the goal of this lecture is to try to explain why an analog of this, a partial analog of this first step makes sense in the p-adic setting, and is interesting in this case from the representation theoretic point of view as well. But I won't be able to say anything about the second step. And okay, because I'm out of time, maybe to finish, let me just say something about step 2 in the case where n is 1. And step 1 and step 2. What happens when n is 1? So what is, okay, first of all, what is burn 1? Well, it's parameterizing line bundles on X, so it's just a Picard step. And this, well, has connected components indexed by the degree. And what is burn prime n? Well, burn prime 1 by definition parameterizes. Okay, so here I think that's what I was worried about. So I think the correct thing is I should take the n-1 tensor product of the dualizing sheaf. So when n is 1, it's just a trivial, the structure sheaf itself that I see. So what I have is just a non-zero section of a line bundle. So I have a line bundle plus a non-zero section. This is the same as an effective Cartier divisor. So what does this burn prime and what does the pullback of burn prime n over this connected component of degree d look like? So here what you have is just this symmetric product of the curve, which parameterizes effective Cartier divisors of degrees. Right? You can think to this as parameterizing a line bundle of degree D and non-zero section, and this maps just under the line. Okay, and then the idea is basically the following. We have L, which is this pure bar sheaf of rank 1, corresponding to our rank 1 Galois representation sigma. And well, first you check that if you take this Cartesian product of L, it will define the least sheaf on this Cartesian product of X. And in fact, it descends to a sheaf on this symmetric product, which is again this. So here you have to use the rank 1 assumption to get for each D. This is for each D. This uses L as 1. Okay. And this map here, this vertical map is just the Abel-Jacobi. Okay, so instead of actually here, okay, what is it that we want to do? We basically want to see that our, let's say when D is 1, we want to see that our least sheaf L and X come via pullback from something on, from a least sheaf on peak 1. Here it's convenient to, because this doesn't change anything as far as L-adic sheaves, L-adic local systems are concerned. It's convenient to replace the Picard stack by the Picard scheme, by the coarse modular experiment. And so you are looking at the Abel-Jacobi map. You can also do it in every degree, right? Which goes from this symmetric product to the component of degree D of the Picard scheme, which I write with a straight capital P. And Deline's wonderful observation is that whenever D is bigger than 2D minus 2, Riemann-Roch implies that this morphism AGD is a fibration in projective spaces. Okay, and why is that useful? Well, we know that the fibers are projective space. We can also assume that we have replaced the problem is eta local, so we are free to replace K, the base field, finite base field K by its algebraic closure K bar. So then we look at the Abel-Jacobi morphism over K bar. And we know that in high enough degrees, by Riemann-Roch, these fibers of this morphism are projective spaces. But projective space over K bar, which is algebraically closed, of characteristic P, exactly like in characteristic 0, is simply connected. So in particular, this tells us that local constant shifts are locally constant shifts are the same on the base or on the target. In other words, this least sheaf LD, for any D bigger than 2G minus 2, where G is the genus of the curve, automatically descends to a least sheaf on peak D. Okay, and then you have to use a little argument using the mosaic property in rank 1 to extend the sheaf you have constructed on the components of degree bigger than 2G minus 2 to all of the Picard scheme. But this is not so difficult. The key observation is really this one, that in high enough degrees, this Abel-Jacobi map is a fibration with simply connected fibers. The case where n is strictly bigger than 1. So this step 2 is much more complicated because the complex of shifts you consider are not like these shifts anymore, but like perverse shifts, and so you have to work much more to make step 2. But at least step 1 is easier. I wanted to explain how to use the L-adic Fourier transform to perform this first step, but I will postpone this to another day.